Hi guys, this is the 1.3 day 1 video. We're talking about continuity and limits. So we started off with this idea of something being continuous. If it's a continuous function, I can draw it without picking up my pen. So there's not going to be breaks, holes, gaps, you won't see asymptotes, stuff like that would not be on a continuous function. If we have a continuous function, then we can find a limit of it. And what the limit just means is if I've got this point on my C, if I've got this point C, where x is equal to C on my continuous function, and this limit exists at that function, then all my y values, as x approaches this point from the left-hand side, all my y values get close to it. And then as x approaches from my right-hand side, all my y values are also getting close to that number. So whatever that number is, it would be L. So we would say the limit as x approaches C of f of x is equal to L, whatever that y value is. And let's see what we're going to do with it. So if we want to decide something is continuous, we wouldn't say, well, it's continuous because I can draw the line without picking up my pen. That's not a very rigorous mathematical definition. So now that we're in pre-calculus, we're going to have to come up with a much more rigid test to determine whether something's continuous or not. So in order for something to be continuous, three things have to be true. We have to be able to say that there's a y value when x is y value for that function. So f of c has to exist at whatever that point is. The limit has to exist at that point. In other words, everything from the left-hand side has to be going to the same point that's going to the right-hand side. So those guys have to meet in the middle at my c value. And then the values of the limit has to be the same as the value of f of c. So that's a whole bunch of words. So let's look at what that means in action, because words just, I'm sure your head is just swimming at this point. So here's the function that they're giving me, and they're asking me to determine, is it continuous at x equals 2? So the first thing that I need to test is, does f of 2 exist? That means if when I put in if I put number 2 into my function, everywhere I see x, I need to get a number spit out, not a nope, that doesn't exist. In other words, it can't make the denominator of a fraction 0, or it can't leave a negative number underneath the square root sign. So here we've got 2 times 2 squared, which would be 8. Negative 3 times 2 is negative 6 minus 1. So 8 minus 6 is 2, minus 1 is 1. So f of 2 exists, and its value is 1. So now we're looking at, does this limit as x approach 2 exist? So here's our table. So as our x values are getting closer to 2, for both sides, we're looking at what are our y values doing. So over here, as my x values are getting closer to 2, my y values 0.5, 0.95, 0.995. Hopefully you can see that the y values. So as my x's are getting closer to 2, my y values are getting closer to 1. And we say that's from the left-hand side. So from the negative side, think of it kind of as the negative side, but negative, that little negative up there means that's the left-hand side. And then we got to look at the other side because they have to be the same. So as we look at the right-hand side of this function, as my x values are getting closer to 2, what are my y values getting closer to? 1.5, 1.05, 1.005. Again, we're also getting closer to 1. So since the left-hand limit and the right-hand limit are both getting to 1, my overall limit is getting to 1. So I can say we have a limit as x goes to 2 of f of x, and that limit is 1. So in order for the limit to exist, the left-hand y values have to be going to the same place as the right-hand y values. They're both going towards 1, so the limit exists, and that value is 1. All right. For number 3, this is the last part of my continuity test. So first, f of 2 had to exist. Then the limit as x approach 2 has to exist. The last part is, do those two values equal each other? So we said f of 2 was 1, and we said the limit of f of x is equal to 1. So this is what we're going to write here. Since limit as x approaches 2 of f of x is equal to f of 2, and those guys are both equal to 1, then f of x is continuous at x equals 2. So the three things for continuity: the function has to exist at your x value. In other words, you have a y value that can be put out. And then the limit has to exist as it goes towards that x value, and they have to be the same. So let's look at number 2. Here we've got a piecewise function. It's defined into two pieces. First, when x is less than 0, and then when x is greater than or equal to 0. So the first step is, does f of 0 exist? We're testing for continuity at x equals 0. So first we plug in 0. 0 lies within this interval because it's got the equal sign underneath it. So I'm going to plug in 0 for x, and f of 0 is equal to 0. So part 1 of my continuity test checks. Part 2 of my continuity test says that the limit has to exist. So let's graph this one real quick. When we are less than 0, we've got this reciprocal function, which looks like this, with an asymptote down my y-axis. And then when x is greater than or equal to 0, we write 0 over here. This is a linear parent function. So this is a reciprocal parent function, linear parent function. If you don't know those yet, make sure you're studying that orange card that I gave you that's got all of your parent functions from last year. It's imperative that you know what they are come test day. All right, so for our limit, our left-hand limit, as x approaches 0 from the left-hand side, as my x's get close to 0, what's happening to my y values? They're tanking, right? Where are they headed to? Hopefully you said negative infinity. So my limit as x gets close to 0 of f of x is negative infinity because it's going down to negative infinity. All right, let's look at our right-hand limit. So now we're looking at the right part of our graph. As x gets close to 0 from the right-hand side, what's happening to those y values? They are getting close to 0. So now here's our question. Does the left-hand limit equal the right-hand limit? No, one's going to negative infinity, one's going to 0. So they're going to two different places. So the limit as x approaches 0 overall of f of x does not exist. Does not exist. So therefore, that's what these three dots mean. Therefore, f of x is not continuous at x equals 0. So again, we checked, did f of 0 exist? It did. Does the limit exist? It did not exist. So since one of my three tests did not exist, did not work, it's not continuous at x equals 0. Let's do one more example for continuity. Here's f of x is equal to x cubed. First check. Does f of 0, because we're talking about at 0 again, does f of 0 exist? That would be 0 cubed, which is 0. It exists. Here's our graph for x cubed. All right. Look at our left-hand limit. As x approaches 0 from the left-hand side, what are our y values? So we're getting closer to 0 with x's. Our y values are getting closer to 0 as well. All right. Our right-handed limit, as x approaches 0 from the right-hand side, so as x gets closer to 0, our y values are getting closer to 0 as well. So the limit from the left-hand side is 0, limit from the right-hand side is 0, they're both the same. So the limit as x approaches 0 of f of x is 0. Check, it exists and it's 0. All right, my third check to see if it's continuous or not, or does f of 0 equal limit as x approaches 0 of f of x? And it does, they're both equal to 0. So we can say f of 0 is equal to the limit as x approaches 0 of f of x. Therefore, f of x is continuous at x equals 0. All right, I'm going to talk about discontinuity in the next video.